In this lecture, we're going to continue our study of bonding and covalent molecules, and specifically, we're going to look at a theory called valence shell electron pair repulsion theory, or we often say VSEPR for short. So, in VSEPR, this gives us a way of predicting what the shapes or the molecular geometries of a molecule is going to be based on its Lewis structure. And so, the geometry around a given atom is determined primarily by minimizing the electron pair repulsions. This is just a fancy way of saying that electrons are all negative, and so they want to get as far away from each other as possible. Any lone pair or any bonding pairs are all going to try to get as far away from each other as possible, and that's what determines the geometry of the molecule. And so to determine the geometry, all we need to do is count the number of electron groups about the central atom. And an electron group is just any lone pair or any bonded atom. And even if an atom is connected to another by a double or triple bond, it still only counts as one bonded atom or one electron group. So with that in mind, let's take a look at the 5 basic shapes that we need to learn. So if I have 2 electron groups, the best way for those to get as far away from each other as possible is if there's 180 degrees between them. And so if I have 2 electron groups, we call this geometry linear. If I have 3 electron groups, the atoms are still, or the electron groups are still all going to be in the same plane, but they're going to be now 120 degrees apart from one another. In the case of 4 electron groups, now the molecule is no longer planar. And the best way for 4 electron groups to get away from each other is to adopt this geometry here that we call tetrahedral. With 5 electron groups, in this case, I have 3 atoms in what we call an equatorial plane, and these are all 120 degrees apart from one another. And then I have 2 axial atoms that are 180 degrees from one another. So in the linear, and the trigonal planar, and the tetrahedral, all of the electron group positions are identical to one another. The trigonal bipyramidal is the first case where these equatorial electron groups are fundamentally different from these axial electron groups. And then finally, the 5th electron geometry that we need to know is when we have 6 electron groups, and we call this one octahedral. And this is characterized by 90 degrees between each of the atoms. And in this case, again, all of the electron groups are identical to one another. So to get a better idea of what these look like, you can go to this link here, and this gives us an online molecular models so that we can actually manipulate these molecules. And so I'm going to close PowerPoint and go to this website. All right, and so this website is pretty cool. So I've got all of my different electron geometries on the right-hand side here. And if I want to see what a linear molecule looks like, I've already got that up. So CO2 is an example of a linear molecule. And so we can see these guys essentially are just in a line, and the 2 electron groups are 180 degrees away from one another. If I want to see trigonal planar, right, in this case, all of the atoms are in the same plane, and they're just 120 degrees away from one another. When I go to tetrahedral, this is 4 electron groups. So this is the first electron geometry that has a 3-dimensional structure. This is the best way for the atoms to get as far apart from one another as possible. And the angle in between each one of the atoms is 109.5 degrees. When I go to 5 electron groups, this is called the trigonal bipyramidal. And so you can kind of see what I'm talking about here. Fundamentally, from a symmetry standpoint, these 3 atoms aren't identical to the 2 here. And so these 3, we say these are in the equatorial plane, and these 2 guys are axial. And so the bond angle between the 3 guys in the equatorial plane is 120 degrees, and the bond angle between the axial and equatorial atoms, as you can see, is 90 degrees. The final structure that we have, this is actually a typo here on this website. This says trigonal bipyramidal, but SF6 is an example of an octahedral molecule, so I apologize for that. And so here's what it looks like when we have 6 electron groups. And so here all of the atoms or electron groups are identical again, and I have 90 degrees between all of them. Or if I rotate it like that, you can see, all of these guys are identical to one another. So I encourage you to visit this website and take a look at what the shapes of these molecules look like. So let's go back to the PowerPoint. All right, so on my next slide, I just want to practice counting the electron groups. So here in this case, I've got carbon dioxide. And so if I count the electron groups on this atom, I have one bonding atom here and another bonding atom here. So remember, it doesn't matter that these are double bonds. Double bonds, triple bonds, they still count as a single bonded atom. So this atom has 2 electron groups. So 2 electron groups means the electron geometry of carbon dioxide is linear. Here I have the Lewis structure for water. In this case, I have 1, 2 bonded atoms and 1, 2 lone pairs. So I have a total of 4 electron groups, and so water has a tetrahedral electron geometry. Finally, I have xenon tetrafluoride. I have 1, 2, 3, 4 bonded atoms and 1, 2 lone pairs. And so I have a total, 4 plus 2 is 6 electron groups. And so the electron geometry of xenon tetrafluoride is octahedral. In our last example, this is formaldehyde. I only care about the central atom. So in this case, around the carbon, which is my central atom, I have 1, 2, 3 bonded atoms. That's no lone pairs on the carbon, so it's only 3 electron groups. So the electron geometry of formaldehyde is trigonal planar. Now in terms of the electron geometries that we've just been talking about, the electron geometries don't differentiate between bonded atoms and lone pairs. But when I talk about the actual shape of a molecule, because we can't really see lone pairs, when I talk about the shape or the molecular geometry, I do need to differentiate between whether my electron groups are bonded atoms or whether they're lone pair electrons. And so let's look at a couple examples. In the case of the linear electron groups, there really is no other options. There's only ever 2 electron groups, and so the electron geometry is always the same as the molecular geometry in the case of 2 electron groups. So linear is actually fairly trivial. But let's see what happens when I go to trigonal planar. So 3 electron groups is trigonal planar. In this case, so the molecular geometries are always subsets of the electron geometries. In the case of BF3, you can see I have 1, 2, 3 bonded atoms, and I've got no lone pairs on the boron. So this molecule has 3 electron groups. It has no lone pairs, so it's got 3 bonded atoms. The electron geometry is solely determined by the electron groups. So anytime I have 3 electron groups, the electron geometry is always trigonal planar. But in this case, the molecular geometry, because I have no lone pairs, is the same as the electron geometry. So when I have no lone pairs, the electron geometry and the molecular geometry are the same. Now when I have lone pairs on the central atom, things change a little bit. So in the case of sulfur dioxide, I still have 3 electron groups. I've got 1 lone pair, 2 bonded atoms, so I've got 3 electron groups. So the electron geometry, which only depends on the number of electron groups, is still trigonal planar. But now, because I have 1 lone pair, the actual shape of the molecule is no longer trigonal planar, right? Because I've got a lone pair sticking out here, but when I talk about the shape, I'm only talking about the shape that the bonded atoms make. And so the molecular geometry, when I have 3 electron groups and 1 lone pair, we call bent. But in every case, first I determine the number of electron groups. That determines the electron geometry, and then the molecular geometries are just subsets of the electron geometry. All right, let's take a look at 4 electron groups. So in the case of methane, I've got 1, 2, 3, 4 bonded atoms, no lone pairs. So if I have 4 electron groups, the electron geometry is tetrahedral. In the molecular geometry, if I have no lone pairs, is always the same as the electron geometry. So both the electron and molecular geometry of methane is tetrahedral. In the case of ammonia, I still have 4 electron groups, 1, 2, 3 bonded atoms plus 1 lone pair. So I've got 4 electron groups, so the electron geometry is still tetrahedral. But now because I have 1 lone pair, the molecular geometry, or the shape, is no longer tetrahedral. In this case, we call it trigonal pyramidal, right? Because this sort of, the atoms kind of make a pyramid, and it's a 3-sided pyramid, so hence the trigonal tri-pyramid. And finally, water is an example of a molecule that has 4 electron groups, 2 lone pairs, 2 bonded atoms. But because it has 2 lone pairs, the electron geometry is tetrahedral because it's still got 4 electron groups, but now when I have a tetrahedral electron geometry with 2 lone pairs, we call that geometry bent again. So they reuse some of these names for better or worse. And one thing that I've actually missed here is the ideal bond angle I haven't been talking about. So let me go back to, so linear, the ideal bond angle is 180 degrees, right? To get as far away as possible, they're going to have 180 degrees. And so the ideal bond angle is always 180. In the case of trigonal planar, the ideal bond angle is 120. So, right, there's 120 between these guys. And if we imagine the lone pair here, there's still an ideal bond angle of 120 degrees. In the case of a tetrahedral molecule, the ideal bond angle is always 109.5, regardless of whether I have lone pairs. The ideal bond angle is always 109.5. When I go to 5 electron groups, so again, 5 electron groups, if I have no lone pairs, the electron geometry and molecular geometry are the same. Now, in the previous molecules, when I had one lone pair, it didn't matter where that went because all of the atoms were identical. But remember, in the case of trigonal bipyramidal, I've got these atoms in the equatorial plane, and I have the axial atoms. The lone pairs always replace the atoms in the equatorial plane. So when I go to one lone pair, as in the case of SF4, we can see that the lone pair replaces this equatorial atom. And we call this molecular geometry seesaw. And so to imagine that, like if we rotated this guy 90 degrees, you can see that that looks like the children's toy, a seesaw, hence the name. In the case of 2 lone pairs, I again remove one of the equatorial atoms. So if we imagine I replace this guy with a lone pair and this guy with a lone pair, I'm left with a structure, that looks kind of like a T, or they've kind of drawn it off to the side here, but they just call this one T-shaped. In the case of 3 lone pairs, again, I take off the equatorial atoms, and so in this case, if I take off all 3 equatorial atoms, I'm just left with the 2 axial atoms, and so that geometry is linear, because again, these guys just fall in a line. All right, and then the final electron group is octahedral. Again, if I have no lone pairs, the electron geometry and molecular geometries are the same. It doesn't matter if I have one lone pair, which one I take off, because all of the atoms are identical. And we call this shape square pyramidal. Because again, if I was to sort of draw sides on these guys, they kind of make a pyramid and it has a square base, hence square pyramidal. When I take off the second lone pair in the octahedral electron geometry, I take the one opposite of the first atom that I took off. So I first replace this guy with a lone pair. Now I'm going to replace this guy with a lone pair. So this ends up being a planar molecule, and it makes a square, so the name is square planar. All right. Now, one thing that we need to talk about when we're talking about these electron and molecular geometries is that bonded atoms and lone pairs are not exactly equivalent. And the lone pairs kind of smear their electron distribution about the central atom. And so they are actually more repulsive than a bonded atom. And as a result, when I add lone pairs onto an electron geometry, it actually squishes the remaining bonded atoms together. And let's take a look at an example for what I mean by that. So if I have a tetrahedral molecule, the ideal bond angle is always 109.5. But in the case of ammonia, that was our case where we had 3 bonded atoms and 1 lone pair. The lone pair, being more repulsive, squishes the rest of the atoms together. So the 3 remaining hydrogen atoms in ammonia get squished together. And so they actually get a little bit closer together because the lone pairs are more repulsive. So the bond angle in the trigonal pyramidal molecules is less than the ideal bond angle. And so in the case of ammonia, it turns out it's 107.3. I'm not going to ask that you memorize these exact angles. I just want you to know that when we have lone pairs, the bond angles get smaller than the ideal angles. And if I add another lone pair, in the case of water, so water's got 2 lone pairs, 2 bonded atoms, so it's still a tetrahedral electron geometry, but the second electron pair squishes these guys even closer together, so the bond angle gets even smaller. All right. Now the last thing I want to talk about is what happens when I have more than one central atom. And essentially, nothing changes. If I have more than one central atom, we don't have individual names for the molecules. I just specify what is the geometry about each central atom. So in the case of ethane here, I've got 1, 2, 3, 4 bonded atoms around that carbon. So the electron and molecular geometry, because I don't have any lone pairs, is tetrahedral. Or this carbon also has 1, 2, 3, 4 bonded atoms. So the electron geometry and molecular geometry about this carbon is also tetrahedral. So I don't have a name for the overall ethane, for the geometry of the overall ethane molecule. I just specify what is the geometry about each central atom. In the case of ethanol, this carbon central atom has 1, 2, 3, 4 bonded atoms. So tetrahedral electron geometry and molecular geometry. This carbon also 1, 2, 3, 4 bonded atoms, no lone pairs. So it's also tetrahedral, tetrahedral. This oxygen, also a central atom because it's connected to 2 different atoms. It has 1, 2, 3, 4 electron groups, but 2 of them are lone pairs. So 4 electron groups means the electron geometry is tetrahedral. The presence of the 2 lone pairs means that the molecular geometry is bent. So let's look at 2 additional examples. All right, so I want to determine the shape or the molecular geometry about each one of the central atoms in this molecule. In this case, I've got acetone. So if I look at this carbon atom first, I've got 1, 2, 3, 4 bonded atoms. I've got no lone pairs. So I've got 4 electron groups with no lone pairs, so that's going to be tetrahedral. In the case of this carbon atom, I've got 1, 2, 3 bonded atoms, no lone pairs. So both the electron geometry and molecular geometry are going to be trigonal planar. And this guy on the right here again, 1, 2, 3, 4 bonded atoms, no lone pairs, so it's going to be tetrahedral for both the electron and molecular geometries. And if I look at this oxygen atom, right, this is not a central atom because it's only connected to one other atom, so I don't need to specify its geometry at all. Let's do one more example. All right, so this is the glycine molecule. All right, so this oxygen is a central atom because it's connected to 2 different atoms. It has 1, 2, 3, 4 electron groups, so its electron geometry is tetrahedral, but because it has 2 lone pairs, the molecular geometry is bent. This carbon atom has 1, 2, 3 bonded atoms, no lone pairs, so both the electron and molecular geometries will be trigonal planar. This carbon atom has 1, 2, 3, 4 bonded atoms, no lone pairs, so both the electron and molecular geometries will be tetrahedral. And finally, this nitrogen has 1, 2, 3 bonded atoms. It has 1 lone pair for a total of 4 electron groups. So its electron geometry is tetrahedral, but because it has 1 lone pair, the molecular geometry is trigonal pyramidal.